I wanted to eat a croissant. So I went to a place that sells croissant. And I bought a croissant. And I returned home with the croissant. And then I ate the croissant.
But are you satisfied with your cosine? Hey Messians, Jim here. And today, we're talking about cosine. The cosine function is a function comprised of the ratios between the adjacent to the hypotenuse of a right triangle formed by a given angle in standard position. Let's look at a graph. Let's look at the graph of a cosine function and judge it like your relatives at Christmas. The period of a graph is when a section of the graph repeats itself. Since this is a periodic function, a section of cosine function will repeat itself over and over. As you can see, wherever you start in this graph, the graph repeats in intervals of 2 pi. Next, amplitude. This is the graph's maximum and minimum y values from the x-axis. Since amplitude refers to distance, we only take the absolute value. And here, you can see it's consistently 1 unit. Since this is the original graph, there is no horizontal or vertical shift. It's periodic and perfect as it is, with no need for change whatsoever. Or is it? Are you satisfied with your cosine? What if there's some natural phenomenon that can be expressed as a cosine graph, but the phenomenon repeats in the course of 3 days and not 2 pi days? What if a wave rises and falls by a difference of 12 inches and not just 1? What if the graph needs a little nudge up, down, left, or right in the Cartesian plane? That's where transformation comes in. By changing the function of the graph, you can transform the properties of the graph. For cosine, we can change the coefficient of the cosine, the coefficient of x, the subtrahend inside the cosine function, and the addend outside the cosine function. Let's name them A, B, C, and D respectively. Changing these values can change the graph. Now how does this work? Let's find out.
Mabuhay! This is Sabrina Katapang from Group 2 Boyle, and in this part, I will be showing the transformation in the graph when the value of a changes in f of x is equals to a cosine quantity bx minus c plus d, where the absolute value of a is the amplitude, b is used to determine the period by using 2 pi over the absolute value of b, c to determine the horizontal shifting, and d to determine the vertical shifting. In the mother graph, where f of x is equals to cosine quantity x, the value of a is 1. Therefore, the amplitude is 1. B is 1, so the period is 2 pi. Both c and d are equal to 0, so there are no horizontal and vertical shifts. The amplitude is equal to the vertical distance between the highest point and the x-axis. In this graph, the distance between the highest point and the x-axis is 1, which is also the same value for a. If we change the value of a, we would see a difference in the highest point on the graph. The new equation is g of x is equals to 4 cosine quantity of x. Because a is now 4, the amplitude changes. The graph looks steeper than the mother graph. We can now see in the graph that the vertical distance between the highest point and the x-axis is 4, which is the amplitude. The value of b is still 1, so there are no period changes, and same with c and d, the value of both is still 0, so there are no vertical and horizontal shifts.
The mother graph is the blue line with the equation f of x is equals to cosine of x. If we change the value of b, the new graph is the red line with the equation g of x is equals to cosine of 2x. The formula for period is 2 pi over the absolute value of b. If the absolute value of b is greater than 1, then the period is less than 2 pi and the function undergoes horizontal compression. If the absolute value of b is less than 1, the period is greater than 2 pi and the function undergoes horizontal stretch. For our new graph, since we change the value of b to 2, we will get 2 pi over 2, which is equals to pi. Since b is greater than 1, then the period is less than 2 pi and the function undergoes horizontal compression. The amplitude is equals to the absolute value of a, or the distance between its highest point and the center line. Therefore, the amplitude for both graphs is equals to 1. For the mother graph and the new graph, there is no horizontal shifting because c is equals to 0. There is also no vertical shift for both graphs because d is equals to 0.
Next, what if we change the value of c in the equation f of x equals cosine x? As seen here, the mother graph is shown by the black graph. The equation of this graph is f of x equals cosine x. If we change the value of c to, let's say, 7 over 4, the graph shifts horizontally because the value of c represents the horizontal shift. As seen in the new graph shown in orange, where the equation is f of x equals cosine x minus 7 over 4, the graph has shifted to the right. To conclude, the amplitude of both graphs is equal to 1, period of both graphs is equal to 2 pi, no vertical shifting for both graphs, and the only difference is the horizontal shift of 7 over 4 on the new graph.
We will now go over changing the variable d in the equation f of x is equal to cosine of x. Its graph is shown in the form of a green line. Changing the value of d will give us our new equation, g of x is equal to cosine of x plus 1. The graph of the new equation is the purple line. We use the formula absolute value of a to find the amplitude of our equations, both of which having a value of 1. To find the period, we use the formula 2 pi all over absolute value of b. Since the value of our b is 1, our period would be 2 pi, similar for both equations. There is no horizontal shifting for both graphs because c is equal to 0. Our original equation does not have a vertical shift because d is equal to 0. Our new equation has a vertical shift, having a value of d equals 1. Vertical shift is how far the function is shifted vertically from the usual position. Here we can see that our new equation shifts up by a value of 1 compared to the original equation.
Changing of f of x is equals to a cos open parenthesis b x minus c close parenthesis plus d. It has several effects. Adjusting a will change the amplitude of the graph, and it also will result in a taller graph, while decreasing a will make it shorter. Modifying b will impact the period of graph and also will compress the graph horizontally, causing it to oscillate more rapidly. If A is increased while B remains the same, the graph amplitude will become more significant without affecting the period. If B is increased while A remains the same, the graph's period will become shorter, resulting in more oscillations. But changing both A and B simultaneously will alter both the amplitude and period of the graph, making it taller or shorter and more or less frequently depending on the specific values that you have chosen. So as you can see, if you change the amplitude to the to our A and B, wait, A is equals to 2 and while b is equals to 1/2. Let's say the amplitude will change into the absolute value of the coefficient, the cosine term. In this case, the amplitude will be 2. Next, in finding the period, uh, with the formula 2 pi over coefficient of x. In this case, the coefficient of the x is 1/2. So therefore, the period is 2 pi over 1/2. Then we will get 4 pi as the period for the period. In this next, the horizontal shift. Uh, by determining this horizontal shift, we'll use the formula, the general form, cosine open parenthesis a times x minus b close parenthesis, where b is the horizontal shift. In this case, there is no x term inside the cosine function, so there is no horizontal shift. Next, in finding vertical shift, I believe that there is no vertical shift because there is no constant added or subtracted outside the cosine function. In this case, there's no such constant or there's no vertical shift. So it equals to 0. So the only function, the function f of x is equals to 2 cosine open parenthesis 1/2 times x has an amplitude and a period, but no horizontal and vertical shift.
But what if A and B aren't 1? What if C and D aren't 0? What if all the values were changed? This is the most tedious of them all, considering that there are period and amplitude transformations, as well as horizontal and vertical phase shifting. Hi, it's me, BB6 Después, teaching you how to graph such functions. Consider the function f of x is equal to 2 subtracted from twice the cosine of 1/2 times the difference of x and 3 pi, which seems pretty complex compared to the graph of just f of x is equal to cosine of x, but bear with me. In here, I like to work from the inner groupings first, and that is transforming the mother cosine graph from horizontal phase shift, then period transformation, followed by amplitude transformation, and then the vertical phase shifting. To make graphing and references easier, remember these points from the graph of cosine of x, as they are what we would move to change the graph. As you can see, there is a horizontal shift of 3 pi, so I can just shift the mother graph's determined points 3 pi units to the right or to the positive direction. From b, I can calculate the period. 2 pi over b is equal to 2 pi over 1/2. This gives me the period, which is 4 pi, so I can just plot the points of each period's endpoints, stretching the distance of the predetermined points. Then I'm given a is equal to -2, which means there is an amplitude stretch by 2 units or 1 unit from crest and throw, as well as a vertical flip of the graph since a is negative. Finally, I can shift the whole graph 2 units down given the -2, and there you go, you have the graph of the example function.